Hey, my name is Ralph Charlesworth. My student number is 43585-214.
Hi, my name is Kanika, student number 4313120. The model that we are demonstrating today is an example of seepage flow through an embankment.
The first experiment that was conducted observed a seepage flow through an embankment consisting of coarse sand. Two trials were conducted, with the first trial tested as a homogeneous sand embankment, and the second trial replaced the toe of the embankment on the downstream side with gravel. The upstream side of the dam was then flooded with water, where the flow direction was able to be observed because of the colored dye that was injected into the sand. In the first trial, it was found that as the water was added, it rose on the upstream side of the embankment and soon reached a certain height where it no longer rose. The embankment on the downstream side of the dam eroded from the base up to the height of the water, hence failing. In the second trial, when the gravel was added, the water reached a higher point on the upstream side, and most of the water was directed through the gravel, which was seen with the dye. This was because the gravel acted as a drainage point for the embankment. This resulted in the dam not eroding like in the first trial and stopped the failure from occurring. The reason the gravel stopped the failure was because it had a greater void space compared to the sand. These gaps allowed for a larger volume of fluid through, as well as creating a faster velocity of water flow. This resulted in an area of low pressure which attracted the flow of water and can be seen from Bernoulli's principle. This flow of water through the base of the dam took the pressure off the sand embankment and stopped the erosion. The gravel also prevented the sand from eroding because it trapped eroded sand between the voids. The second experiment that was conducted was the consolidation test. This demonstrated the effect of loading on saturated and unsaturated soils by measuring the water height in a piezometer tube due to the weight applied on the soils. 3 trials were conducted. These were water by itself, fully saturated gravel, and fully saturated rubber granulates. It was consistent in all trials that as more weights were placed onto the apparatus, the water pressure and pore water pressure increased. This effect could be seen from the water in the piezometer tube, which rose with each weight added. This is because the water took the majority of the applied stress. The pressure in the piezometer tube can be found using the equation ρgh equals force over area. Once the valve was opened, the water in the piezometer tube decreased, releasing the built-up pressure caused by the weights. This occurred because when a soil layer is subjected to a vertical stress, volume change takes place. However, the volume of soil grains remains constant, so the change in volume must come from the change in pore space, i.e. the loss in water. This loss can occur over long periods of time, unlike in the experiment where it happened very quickly, and depends on the porosity and permeability of the soil. This decrease in water content in a saturated soil is called consolidation. This experiment can be compared to real-life situations of soil mechanics, such as soil compaction due to discharge in different soils. When comparing rubber granulates to clay, even if the two have the same stiffness, the rubber contains more void space between the particles. Therefore, when the rubber is under compression due to a load, there is more space for the compressed particles to fill, and results in differential compaction.
This test was designed to determine the effect that water and gravel can have on slope stability. The experiment consisted of a 60 cm long board which was lubricated with water and had a hinge at one end so that it could be tilted. A cylinder was placed on the surface of the board and filled with varying amounts of gravel and water. The contents of the container were altered slightly in each trial of the experiment. These variations including changing the water level between 0 mm and 150 mm, and the gravel between 0 mm and 100 mm. The board was then tilted until the container overcame the static friction, and the angle was recorded. This was repeated 3 times for each quantity of gravel and water, with the leaking and non-leaking container. As demonstrated by the experiment's footage, the board was raised at one end in order to increase the angle of inclination for the container. The container only began to slide once the frictional force had been overcome by the forces acting on the container, i.e., poor water pressure and gravity. From this result, it was concluded that the lack of stability in the leaking containers is due to the water pressure acting downwards onto the board. Although the quantity of water that was leaking was negligible, it was enough to add a significant force into the static equilibrium. This seemingly insignificant leak creates a small lifting force, thereby reducing the weight on the slope and thus reducing the frictional forces involved in maintaining the static container. The results from the leaking container were highlighted, as can be seen in Figure 1. These results would indicate that all leaking containers had a lower stability angle in comparison to the non-leaking containers. Additionally, as the mass increased, the angle appeared to decrease in Figure 2. There was no clear trend shown in Figure 3. The weight of the model affects the magnitude of the normal and friction forces acting on the cylinder. Under equilibrium, the shear force must be equal to the driving force, assuming no cohesion in water pressure. The equation above simplifies to the frictional angle of the soil equaling the angle of the inclined surface. Any angle larger than the frictional angle results in the failure of the soil. Thus, if the weight is increased, the frictional force is also increased and overcomes the shear force, causing the cylinder to slide. If enough weight is applied, it could also result in failure, as it would increase the value of the angle of the inclined surface to be greater than the frictional angle.